Okay, so welcome to this week's seminar. Today we have the pleasure to have with us Dr. Leonardos Gkouvelis. Leonardos Gkouvelis is a staff scientist at LMU in Munich, and he works on phenomenology of exoplanets, rocky exoplanets. He studied physics at the University of Crete here in Heraklion, and then he moved as no, he studied physics, and then you did your PhD in Valencia in Spain, and then he moved for two postdoctoral positions, one at the University of Liège in Belgium, and then, as we were discussing before, he moved at the Ames Center in California, in the US, as a NASA postdoctoral fellow. And now it's an LMU, and today he will be talking to us about towards a meaningful characterization of rocky exoplanets. So whenever you are ready.
Okay, Tanya, thank you very much. And basically, thank you for accepting my self-invitation to this seminar. Last time I gave a talk to your institute was like 15 years ago when I was presenting my bachelor thesis, which Pablo was my supervisor then. And we worked on high mass X-ray binaries. Of course, today I'm going to talk to something completely different. Having in mind that there is practically no one there that works on exoplanets, right? So I will present work that we have. It's basically summarizing some publications we did a few months ago, me and my collaborators, which I show you here from various institutes. Generally, whenever I have seen an exoplanets talk, almost everybody starts with this demographics plot, who shows the known exoplanets that have been detected so far. So I will start the same. You can take many messages from this plot, but I want to focus only on a few. The first thing is that this plot is heavily biased. I have overplotted here the solar system planets, and you see that all of the known exoplanets, or almost all of them, are in very, very close orbit. And this basically is just because it's much easier to detect them. First, because if they are orbiting closer to the host star, we have much probability to see a transit, so we can detect them. And the other one is, as they are much closer, they are hotter, so it's brighter, so it's easier to detect. The second one is here that if this sample here, it's the more rocky exoplanets that I'm going to concentrate in this talk. I'm working with all the planets, by the way, but I'm particularly interested in these smaller ones with around the size of the Earth. But another thing I wanted to focus is that how misleading was for us the solar system. You see, in the solar system, there is a clear dichotomy in the population of planets. You see on the one side, we have the rocky ones, right? Like Earth, for example. And the other one, we have the gas giants. So the question was that, okay, is this a clear dichotomy in the nature or not? You see here in this population that it's not. And actually, we know now today that there are objects in between of them. And I will show you later a plot that basically this is the majority of the planets in the universe, which we don't have an example in our own solar system. And another question I want to make here is that for these planets which are rocky, and what happened in the between, we don't know exactly how it's their nature, if they have a rocky surface, etc. But for those ones which have sizes, let's say, similar to Earth or less, which we know that they're rocky just because we know their density. As you see here, they live very close to their host stars. And then the question arises here is that, can they sustain atmosphere in these harsh environments? So this is a profound question which has implications to what we call habitability, etc. Right? Now I'm going to show you a normalized plot who shows you the population of at least known exoplanets, in a sense, in an unbiased way. You see now that the gas giants here are practically a very, very small percentage if you check here in this plot in comparison to the previous one. Well, what you see that from the known exoplanets, it's a very big population. And this is just simply because they are too big, so they can be detected much easier. Here in this plot, I also show again what would be the size of our own solar system planets. And you see here again the dichotomy. And while this peak is somewhere in the between, which means that sub-Neptunes and super-Earths are practically more abundant in the universe than the rest. So going forward, this was of the known detection, and in the next few years, the predictions are very, very optimistic with the new missions that are space. People expect to detect orders of magnitude more exoplanets, including small ones, rocky ones. And this would be an exciting period for exoplanets, but this is only the detection of them. If we want to focus now on the characterization of exoplanets, which means we have to actually observe their atmospheres and learn something more, since we cannot send a probe there, right? It's very far away. The view in the characterization of the atmospheres is completely different. Because to characterize the planet, to observe the atmosphere is a painful process. We have to go case by case. It requires a very big observational time. Oh, if you hear this, apologies. So it requires a very big observational time, and then the analysis too. It requires a very big computational time with something which is called the inference method. So what is the atmospheric characterization? Everything that this community, this science field wants to do, I can describe it in this simple cartoon here. What we basically want to do is, once we take the observations, in that cartoon here, a spectrum, for example, we apply a methodology which is called atmospheric retrieval, which this is based on Bayesian inference techniques or with machine learning techniques, which the community have adapted from cosmologists or even from medical imaging, for example. And from them, we can infer the atmospheric composition, the thermal structure, and other physical properties of the planet. And then we can, with this, we can make the interpretation about the climate, the formation, history, etc. So focusing now specifically on rocky exoplanets, I would summarize the ideal characterization would be these basic three questions, not necessarily in this order. But the first one is, does it actually have an atmosphere, as I told you before, or it evolving in time just stayed a bare rock, like, for example, the moon, let's say? If yes, is its climate habitable? Whatever habitability means for you, there is no strict definition of habitability at this point. You can think of the conventional way, if it can have liquid water on the surface, but actually we know organisms on Earth that they can survive in very extreme conditions. So there is no strict habitability definition, but if you want to assess the habitability, you need to know physical characteristics of the planet. Now, if the answer is yes, it can be habitable, but does it actually contain, let's say, some life form there? This is a very controversial topic. I will come back again in my final slide. But my main approach here is that if you can observe some physical characteristics of the planet, does this observational signal deviate from what we call the abiotic baseline? If yes, you might start chatting about, okay, maybe this planet is interesting. If no, okay, it can be habitable but uninhabitable. Now, where the community is at this point, we are very far away to talk about habitability or biosignatures, actually. But where we are, it's in the first question. The question is that can small exoplanets, or can we detect if those small exoplanets have an actual atmosphere or not, especially when we know that the population of the known exoplanets are very close to the host stars and are basically all of them tidally locked, which means the star is seeing one of their sides always. Now, some things about how we observe them, right? So imagine this cartoon is an exoplanet system with a host star and the exoplanet. Of course, in your telescope, this would be a point source, right? You cannot, at least in the 99.9%, you cannot separate those two. So the ideal case is to be actually in transit, which means to make a transit for this reason that we do photometric or spectroscopic follow-ups, like in very short times, and then we observe the modifications in the light, right? So if the planet is eclipsing the star, so we call this primary eclipse, and then we can construct a transmission spectrum here, which basically, you see it has the form of what is the fraction of light obscured from the star at this given wavelength. That's simply because sometimes the light penetrates deeper in the atmosphere in some wavelengths and much higher in the atmosphere in other wavelengths. This is how they interact with the constituents of the atmosphere, right? The molecules. And the other mode is we directly take a spectrum, the combination, both the host star and the exoplanet, and we call this emission or thermal emission spectroscopy or photometry. And how we can do this is that we take in observations when the planet, for example, is close to the secondary eclipse, where secondary means that the exoplanet goes and hides behind the star. We take a spectrum or a photometry here, and then once the exoplanet hides behind the star, we take another spectrum, and then we do the contrast. That's why those spectra has this type of form, and we call them like a thermal contrast. Of course, the brighter the exoplanet, the more signal and more easy. That's why small rocky exoplanets are very difficult to observe in both modes, actually. So to solve this first question, where the state of the art right now is, okay, so if we take a specific system, a given system that we want to observe, if we want to solve this degeneracy, we kind of want to cover all the possibilities that this planet can host. For example, if it's a bare rock, we can have to try many different scenarios of surface materials, for example, what kind of synthetic spectra would be generated from this scenario, and what kind of an atmosphere can survive in this planet. And again, try to make hundreds or thousands of spectra scenarios and try then to create some observational strategy to unambiguously distinguish between those two. Indeed, this is the state of the art currently in the community. What I'm showing you here is only one example of a Nature paper in 2023. There are many of them, many in Nature Astronomy and other journals, but this is only an indicator that this topic is really hot right now. And what you can actually see here is the observational point from James Webb Space Telescope is this red point. Yes, only one photometric point. And this, you see here an emission spectrum, so a thermal contrast spectrum that was constructed for this system, which basically shows you the spectrum of the planet, synthetic spectra, right? Which they try to cover scenarios that will match this point. You see, for example, here this dark curve is what is called an ultramafic rock. So as if the planet, the rocky planet, was only a bare rock having this specific material, which is kind of a volcanic material. And they try to match this. The thing is that this type of comparison, of course, is nice for a first reaction to this data, but how they provide this modeling is by taking, for example, atmospheric compositions by hand and put them there and see how the radiative transfer would look like. So it has math, but it doesn't have physics. So what we want to go one step further and check this is, for example, those atmospheric compositions feasible in this planetary system? And if yes or if not, what is the overall scenarios that could be feasible for this planet? Which this, of course, goes much further. You can go how the atmospheres are generated in rocky planets and how they are sustained there and how they lived in long-term geological timescales. So then this brings us back here, and what we finally want to do is the following. It's to provide, to cover a very big, to explore a very big parameter space of these two scenarios, of the bare rock scenario and the atmospheric scenario. Unfortunately, those two are completely, say, at least so far in theory, disconnected to each other, so we have to treat them distinguishedly. So we have to cover a very big parameter space in the bare rock, which means just I'm taking compositional scenarios of the surface of the exoplanet, making combinations between them, and try to provide synthetic spectra. And on the other side, I'm trying to provide atmospheric scenarios, but in a physical manner, which means to solve the chemistry, the photochemistry, and any kind of physical processes in this system that can sustain a composition that actually finally you could create a spectrum and try to see what the telescope could see. Okay, I will not say details here, but I'm going to attack first the bare rock scenario, right? And as I told you before, in this imaginary system, imagine that there is the host star and exoplanet, and as it orbits around the host star, you can take observations in many angles. Of course, the current strategy is to take the combined spectrum exactly when the exoplanet is about to do the secondary eclipse, or even make an integration of the spectroscopy for some angles before goes to secondary eclipse duration. You can, of course, for bright exoplanets, you can take many observations and you can construct something which is called a phase curve. For example, a known object in our everyday lives is the moon. We can take the moon as an example, and we can observe it in many different ways, or we can even model it, and we can construct this type of phase curves from 180 degrees to 0 degrees, exactly on the opposition, right? When it is a full moon. Now, how I model this is as if the surface of the moon, this is a model, right? So I'm assuming here that the surface, all the material that the moon has, it reflects uniformly in space, right? So this is what is called a Lambertian sphere. And the phase curve would look something like this. Now, of course, the reality is not like this. So what I'm going to do now is I'm going to take real material of the moon, there is, right, from the Polo sample return, or even similar materials to Earth. People measure these materials on the laboratory, and they provide you some kind of optical and photometric properties. So you can introduce this to your model, and you can see here the differences in the phase curve. This basically is the state of the art right now in exoplanets, right? Now, what happens if I overplot here the actual empirical phase curve? You would see that it kind of matches what is when I'm using the real material to model, the real properties of the material. But when you go very close to the opposition, you see that there is a very sudden bright. This phenomenon, it's called the opposition surge effect, and it's basically known as a phenomenon like, I don't know, 150 years ago. And basically, by coincidence, the first that explained this phenomenon was the director of the institute I'm working right now at the University Observatory in Munich. It was called von Sillinger. And this phenomenon is called also von Sillinger effect. Anyway, so this phenomenon, we know now that it's a combination of two phenomena. One, it's called the shadow hiding. It's just that when you look, when the light comes in a big angle and reflects to the surface, the surface depends on the grain sizes, will create some kind of shadows. While when the light comes totally vertical, in a vertical angle, those shadows are not there anymore. So that's why it's called shadow hiding. And another contribution there, almost equally and sometimes more important, is something which is called the coherent backscattering effect. It's how to say, it's a quantum mechanical effect where there is two waves traveling in a different direction. They enhance the amplitude of the wave. So that's why this contributes to the brightening. This is completely omitted in the exoplanet community, and it's worse, even worse than this, because right now I'm showing you here an example in a specific lambda 1 band. Now what I'm going to do, I'm going to zoom close to this position effect, and I'm going now to plot 3 different bands, which you don't need to care which bands are, but you see that then this is a phenomenon that it's a function of wavelength, right? Sometimes it's almost negligible, sometimes it's mild, but sometimes it can be really important. Now, why this matters, right, in the exoplanet community? Because you understand that if you're going to evaluate the secondary eclipse depth, which is called, or this emission spectroscopy, very close to the secondary eclipse, if you don't include this phenomenon, you're going to be off sometimes 20, 30, even 50%, depends on the band. Now, of course, the question is, okay, at which angles do you evaluate this phase curve in exoplanets? So far, where people were observing exoplanets, it was mostly gas giants, like this one, for example, which is very close to orbit. And when they are very close to orbit, this secondary eclipse ingress angle, it's actually very high. You see here that in this cartoon I'm having here, that for some famous exoplanets is about 20 degrees. This is 15 degrees, where this opposition effect is not important. But when we are entering to the to rocky exoplanets, specifically more temperate ones, like the TRAPPIST-1 system, or even Earth, I'm showing here Earth as an exoplanet, you see that actually the evaluation is going to be very close to zero, so very close to the opposition. So it actually matters to include this effect. This effect in the solar system science, of course, it's known, of course, it's included, but for some reason, it's actually ad hoc. And my understanding here, I don't know, but my understanding is that in solar system planetary science, the observations are very good. So you take a phase curve, for example, of an asteroid or a comet, you immediately know the shape of the surge, so you can ad hoc it to the. So the modeling was not detailed in a sense, not wavelength dependent, etc. But for exoplanets, we cannot do that, right? We are totally agnostic of the system of the exoplanet. We don't know even if it has an atmosphere or not. So the modeling we have to provide, it has to be based on an assumption, of course, but for that assumption, we have to include all the characteristics a priori. So I did a work which I published a few months ago on this. I published the formulation of an analytical model. So it's a radiative transfer of how the particles behave in a wavelength-dependent manner in this opposition surge effect, combining the shadow hiding and coherent backscattering effects together, which I can actually fit pretty well. You see here the curves of the moon, with a hint that for the moon we have very, very good laboratory measurements, which for other materials, which we call planetary analogs, they are not so good. We have many few. So, but anyway, you cannot escape this phenomenon. So somehow in the future, somebody has to do these laboratory measurements, and then you can start doing more detailed modeling. So having covered all of this, we can now have synthetic spectra of how different scenarios of bare rocks could look like. And I'm showing you here only a subset of them. And now we are going to attack the most difficult one, because this bare rock synthetic spectra is a radiative transfer problem, while the other one, it's a more complete problem, which you will see it includes interdisciplinary knowledge. Now, when we are talking about the atmospheres of exoplanets, if we have in mind a gas giant, for example, like Jupiter, uh, gas giants normally form in regions, at least in the more simple explanation, in the protoplanetary disks, which are farther away from the star and they are colder. So once they formed, they are big and they actually contain the information of their birth, right? So they are mostly nebular gas contaminated with a few higher metals, which if we detect with our telescope can tell us something about their formation time. Now, for the rocky ones, it's not so simple. When they form closer to the host star within the disk, and because the condensation temperatures of metals are much higher, so metals come together and form like silicates and a rocky core in the beginning, and only a small part of nebular gas will be there added to this rocky core. This, of course, will be lost very fast because we are talking about hydrogen and helium here. It's very, and I will explain later why this is lost very fast in the birth of the planet. And then this hot rocky planet stays behind, and the atmosphere that is generated later, it becomes from which we call secondary atmosphere, because it comes in later stages in the lifetime of rocky planets. It actually comes from what we call magmatic outgassing, which means that this hot magma will evaporate gas, surrounding the planet, and even much later even if we create a crust to the planet, even much later we will have this outgas in the planet. We see that example, for example, on Earth, right? We have volcanic activity across all of the lifetime of the Earth. And of course, what kind of material will be outgassed and what kind of secondary atmosphere you would have in the rocky planet, it totally depends on the chemical inventory you would have in this, let's say, melt, in the interior melt of the planet, which of course depends on the initial conditions on the formation history. Now, of course, this looks very tedious, right? This messy thing, and it is. It requires a lot of time and many different, say, different scientific fields to combine together in order to model this, from geochemistry to astronomy and additive transfer, etc. So now we published a framework which it can do this. It can model the generation of secondary atmospheres only based on a few parameter inputs, which I will explain later. The novelty here in our framework, it's actually that we couple atmospheric processes. We try to do as detailed physics in the atmosphere as possible here. But the novelty is that we couple the lower and the upper boundary together. And this is actually not trivial at all, because imagine that the timescales are totally different. The timescales in the atmosphere can be hours to months, while the lower boundary here, the interaction with the interior of the planet, it's in geological timescales. Now, once we have this framework and we can simulate, and we can find the statistical steady state of each scenario that we want to simulate, then it's actually very easy to produce synthetic spectra of the atmosphere, because we just need to solve the radiative transfer, right? Now, something again I wanted to add is that for giant planets, they have all the easy things to do. They are easy to detect. They are very easy to model because they are mainly composed of hydrogen and helium, right? And some contamination of heavier metals. In exoplanets, we call metals everything heavier than helium. But then for the ones that we know that they're actually very hot one, you can make some assumptions or their physical processes inside the atmosphere. For the rocky ones, everything is more difficult. It's very difficult to detect them. For for many reasons. Their mean molecular weight in the atmosphere, it's really actually really high. And the processes that you need to do there, it's very difficult. So you cannot take assumptions, for example, of an equilibrium chemistry, but you have to apply full chemical kinetics. And here, what I'm showing you here is just describing that in the initial state of the rocky planet, there will be some outgassing, which this would be hot gas, because we're talking about the melt will be in the order of more than 1600 Kelvin. This gas will get released outside in the secondary, in the atmosphere. It will cool down, and then you have to do all the atmospheric processes of chemistry. These molecules, they will interact with the light from the star, etc. There will be dynamics. So it's a really messy thing, but luckily it can be dominated. And once you have some secondary atmosphere, another very critical question here is the following. Can this atmosphere that you have just generated for this planet can be stable in the planet, or you will generate the so-called planetary wind? Planetary wind is exactly, in mathematics at least, is exactly the same as the stellar wind, or the Parker wind that you know for the people who study the stellar winds. And it's basically that if the energy that is in the incoming energy that hits the atmosphere can be actually be managed by the atmosphere, or it will generate a regime which is called hydrodynamic escape, and it has a continuous flow of gas to space, which is for planets we call it planetary wind. And I will show you that this is very important for the evolution of the planet. So just few things that even if an atmosphere, it looks very messy and there are many processes, etc., we can boil it down to these parameters. For example, from observations for a specific system, we can constrain some parameters, which is very general for the exoplanet. There are errors, of course, but we can have some constraint. And then in our modeling here, as we designed it, we have this basic unknown. So if you give me these parameters here, I can generate you what kind of an atmosphere this rocky planet would have, but in a completely abiotic form, right, with no life there. So few things. If there is some jargon here, please stop me and ask me, because I understand there are completely different fields, so something might be very confusing. So when I'm saying the surface pressure, I'm saying here it's an indicator of the total mass of the atmosphere. So it's the pressure that in the interface between the surface of the planet and the atmosphere it has. What is the pressure? This is important because you have to imagine that in very high pressures, gas material dilutes within the planet. The redox state is basically the redox state of the interior of the planet, which basically tells you what kind of constituents you have. Is it more hydrogen or is it more like oxygen and carbon bearing species? The graphite activity, it's basically one parameter that tells you from this material that you have in the interior of the planet, the graphite, what kind of percentage is in liquid form and what kind of percentage is it like microcrystals or rocky form. And the melt temperature, of course, is what is the temperature in the interior of the planet. So these here are the big unknowns. There is no possible way at this point that somebody can have some constraint on this. So what we can do is make a parameter exploration, right? But now what I'm going to show you here is we can play a trick, so we can choose correctly a specific planetary system, so we can reduce these parameters. So if we have some kind of constraint on the interior of the melt temperature here, how we can do this? So I will show you here a specific case study that we did for this specific rocky planet, which belongs to it's a newly discovered planet. It belongs to a system with a host star is an M dwarf, and it has 3 exoplanets here. This D planet here, you see here, it's about the size of the Earth in radius and mass. And this C here is a sub-Neptune, so it's a planet a bit smaller than Neptune. And due to the configuration, the orbital configuration of the system, we can estimate the tidal forces that apply to this planet D here, which we are interested in. And then what we can do is we can do the following calculation. We can treat the tidal heat flux that drops in the planet as a heating source, and then we can assume convection in the interior of the planet as the cooling source. So then we do some modeling here. For example, here in the x-axis you see the temperature of the interior of the planet, and here you see heat flux. And then here what we try to do is the blue here, it's the cooling, and this curve red or dark, it's the heating from the tidal flux, right? So what we do is that when they equal together, we say that, okay, this system reached some kind of a steady state, and then we can take the assumption that this is the interior temperature of the melt. And some information here. At 600 Kelvin, the melt, at least we know from laboratory measurements from the Earth, that for less temperature, it's kind of a solid interior, and here it's a liquid interior. We apply here two different models. You don't need to know all the details, but the more sophisticated is the red one, which treats all of the fluid dynamics in the interior of the planet. And what we show here is that the scenarios that are possible for this planet in the interior is that the temperature of the melt would be more than, let's say, 1700 Kelvin. And you see here that this is much higher than the Ios volcanic activity. So in a result, we can guess that this planet can have highly volcanic activity on its surface. Now, okay, you tell me you outgas, from the interior and to the surface and in the atmosphere, you outgas some material. I'm showing you here the model. So imagine, I'm showing you only an example. Here on the x-axis, there is a parameter which parameterizes the redox state of the interior. And here on the y-axis is basically the what's called the volume mixing ratio of the composition of the outgassed material. For example, all of these molecules together. What does it mean? It means that imagine I am starting a simulation and I'm choosing the redox state to be -4, right? This is a log scale, by the way, log. So I'm taking the redox state -4. Then the outgassed material would be, this type of composition. You can draw a vertical line here, right? And then for more oxidizing conditions, it will be a totally different scenario. I understand this might be confusing to you, so I'm going to redraw this same plot in a different way that you as astrophysicists maybe you are more comfortable. So here what I'm showing is the same. It's the redox state of the interior of the planet, and then on the y-axis I'm just showing you the mean molecular weight of the outgassed atmosphere, right? So this has a very profound information here. You see that the mean molecular weight starts from about 2, right, which is more or less close to the nebular gas or what giant planets have. And for more oxidizing interiors, this can reach up to 40, 50 mean molecular weight, so this is totally different, right? But that means that you can have a rocky planet that can generate a secondary atmosphere, which can actually look like the atmosphere of a gas giant, right? Now, what I'm going to show you here, and then now the plots are getting even more busy, I'm going to show you once this material is outgassed above the surface of the planet, now the processes start going on, like the gas is cooling down, chemistry, dynamics are playing a role, the radiation from the host star comes, photodissociates, ionizes. So all of these are taken into account in the atmosphere. And what I'm showing you in this 2D plot here is scenarios of the interior redox state of the planet, then some scenarios covering a big parameter space in the surface pressure, since I don't know this parameter, and the outcome would be the mean molecular weight of the secondary atmosphere for the total of the atmosphere of the planet. again, you see something similar. You start from something which seems very similar to a nebular composition and comes down to what it seems like, for example, for the Earth, Mars, or Venus, right here. This is the total of the planet. The color is the mean molecular weight, by the way. Now I'm going to define another concept here, and this would be, I will just follow my cursor because this slide is very busy. So within the atmosphere of the planet, I will choose a specific layer in the atmosphere, which I'm calling RxUV. And what this basically is the layer of the atmosphere that the radiation that comes from the star, the high energy radiation, will actually get deposited there. Or in other words, is where the optical depth of the high energy radiation of the star will reach unity, more or less. That's very important because the atmosphere will get a lot of heat at this layer, and then the atmosphere with radiative processes and dynamical processes, like for example, work done like PDV, will expand and will try to cool itself down, right? Now the question is that if the atmosphere will manage to cool itself down, maybe it will inflate, but it will be a stable atmosphere. If these radiative processes and expansion, for example, this PDV work done to the system, this expansion that will create, it will actually reach what is called the supersonic critical limit. It will create a steady flow of hydrodynamical flow of the gas that will actually will get lost constantly to space, right? Now, why is this is important? Because if the atmosphere is stable in a material that can lose, all planets lose material to space. For example, Earth is about 1 to 3 kilos per second, right now. And for this case study we are working with, if the atmosphere is stable, it will lose again 3 kilos per second. But if the wind regime is produced, it can reach 10 to the 5, 10 to the 7 kilos per second. So this is a huge number, which actually, even in the back of the envelope calculation here, we can do, if we have the age of the system, we can calculate that that the planet will lose all the initial volatile budget it has in its interior, even if it constantly replenishes, the atmosphere. If you cannot stabilize your atmosphere, you will continuously lose more or less in this rate, and you can actually saturate yourself in volatile. So you can stay just a bare rock. This is also another, first time we present this result in the community. And this plot, what does it show? It shows you that something very profound, that if you have interiors, if you start with these initial conditions, like very reducing interiors, you will generate secondary atmospheres that are very reducing, and they can actually, they are not stabilized in your lifetime, and you can actually, across your evolution as a planet, you will dry out from volatiles, right? And you will stay a bare rock. But if your initial conditions are more oxidized, and I show you here the parameter space where the atmosphere is stable and where it's the wind regime, if you live in this interior state regime, you can actually have a stable atmosphere, and you can sustain it, right? You can sustain it. Then this has many implications on habitability, etc. Nevertheless, this is not only a function of the mean molecular weight I'm showing you here. It's also a function of the activity of the star, right? Because of course you know much better than me that in the beginning of the M dwarf, for example, the star is very active in the XUV, and then drops down. So this is a game that you have to take in account both the planet and the star, right? Okay. Now, once we have all of these atmospheric scenarios that I described you very briefly here, we can generate, again, we can just solve the radiative transfer both in emission or transmission spectroscopy, and we can generate all of these atmospheric scenarios. Here I'm just showing you a subset of them, which here the color just shows you in a interior composition, what kind of redox state you are in your interior as a planet. And what you can do then, you can go back to what the people in the community are doing in the literature, right? In the recent papers, for example, they are proposing to photometrically observe these rocky planets with James Webb and take only one photometric band and try to see if this is possible. That's what I'm doing here. I'm taking all of my scenarios here, which I tried, and what I'm saying, okay, I now try to imitate how would the telescope would see this. I'm choosing the 15 micron band because this is what the observations are happening now. And actually, right now, as we are talking, there is a campaign observing the planet that we have predicted here in this work. And I show you here, for example, on the left, on the y-axis, basically for both plots, is the secondary eclipse depth of this planet as a bare rock. And then on the right, I show you a subset of the scenarios of this planet having an atmosphere, but with different scenarios of its, internal redox state. You see here, I don't include estimated errors here in this plot because it's actually really obvious that there is degeneracy here. With only one photometric point, you cannot distinguish between if it's a bare rock or if it's a planet, it has an atmosphere. And so I'm showing you here different atmospheric scenarios. The colors have different surface pressures. And actually, these rings are the atmospheres that we calculate that they will be actually surviving atmospheres in this system. But still, you see that it's impossible to distinguish only with one photometric band. Of course, you can play this game. You can start adding photometric bands. There were some recent works that they tried with 2 photometric bands. And long story short, even with 2 photometric bands, we cannot distinguish, you cannot solve this degeneracy. In this work that we published, we predict that if you use 3 photometric bands and you create what you astronomers call a color diagram, you can actually distinguish between the 2 regimes. And what I'm plotting here is that you see here in this plot that all the bare rocks scenarios, and which I'm showing you here in colored stars, and I can add much more, but would not make any difference, will cluster in one corner of the plot. Then the more reducing atmospheres will follow this curve, but the actual surviving atmospheres of this system will be on the other end of this plot. So you see that there is a clear distinction now. If you use 3 photometric bands, which those bands here I'm showing you, they actually exist as photometric bands in the James Webb Space Telescope. And something here which is a surprising result for us is that the only thing that matters in this distinction is the redox state so the chemical inventory of the interior of the planet. The surface pressure and the graphite activity, that doesn't actually matter for this observability. Of course, now you would say, okay, this is the gas, right? Or for example, an exoplanet atmospheres person would say, okay, you are making this prediction taking into account only the gas, but real planets are more complicated. They have clouds, right? And they have hazes. Hazes are small aerosols of various sizes in the atmosphere, which are not clustering like clouds, but they are diffusing the whole atmosphere. So we included this. So I'm showing you here the same plot, basically, where the clustering of the bare rocks is here. All of this black curve is only the gas. And then all of these different curves, which you don't need to care, but they show all types of combinations of clouds and hazes that this planet can produce in its atmosphere. So we cover a very large parameter space and show that the actual space that the surviving atmospheres would be, it's this shadowed region. Now, what we predict here is an actual, if James Webb would actually perform these photometric observations in these 3 bands, and then with propagation of the errors, you see that this is only 1 sigma detection for this specific planet. Could be somewhere here, and even on the right, all of this you could detect it in 1 sigma. If you go to scenarios which are closer, you would be within the error, and you cannot have any clear detection. This is a case study, of course. This is for this specific planet. We haven't tested this for more bright planets to see if you can distinguish for all of this space here. But I would say that this is one, if it's not the only, it's one of the few methods to actually solve this degeneracy. Now, okay, this was too long. Now I will close with this. As I promised you, I will go now to this controversial topic of biosignatures. So biosignatures, by definition, is some signal in your telescope that will indicate the presence of biological activity in a planet, even if it's rocky, even if it's gas, whatever you have in your imagination. The thing is that the community right now, what they are trying to do is, which I call, very, let's say, in a way that this is kind of a brute force. So they say, okay, what kind of biosignatures we have on Earth? Let's say it's a combination of few gases. And then, very Earth-centric, they try to apply this to other planets. Of course, there is no known biosignature, or there is no proposed biosignature today from one group that they cannot be reproduced totally abiotically from another group. What I'm just trying to say is that methane, okay, here on Earth may be created from life, but on another planet, it can be created from a rock itself abiotically just fine. And anything else, even this red edge in the photometry, that this famous red edge that the plants, the trees produce here on Earth, we can reproduce it with a total bare rock with a semiconductor, for example, a material which can be like a semiconductor. So there is no distinction of biosignature of what is it. So it's an open question to this point. But what I'm trying to approach here is that before we do any bold claims on what biosignatures are, or if we have detected it in an exoplanet, what we should care now is that what would be the abiotic baseline of this planet? What is the capacity of the planet in covering and in reproducing atmospheres or any signal to our telescopes that can be total abiotic? We should explore all of this parameter space. And then if we see some kind of deviation in our signal, okay, let's talk about it, right? So all of this modeling that we were doing in this framework and in our works, it's processes that are totally abiotic. Now, as in the beginning of my slide, I told you, all of the known rocky planets are very close to their host star. And the majority of them, they have equilibrium temperatures that are about 500 Kelvin, 600 Kelvin, 700 Kelvin. So we can take a big sample of them, and we can all agree that, okay, in these high temperatures, let's say, activity from biological life is not operative, right? So we have to take this population of exoplanets and test our theories, make observations, see, and study the abiotic baseline, the capacity of a planet to produce abiotic signatures. And once we have this, okay, we can go to more temperate planets with biology might be operative and we might have some chance, and then simulate the abiotic baseline, have some certainty about it, and then compare it with the actual signals. And with this, thank you very much. I finished. I will take your questions.
Thank you. Thank you very much, Leo. Impressive. So, time for questions. If anyone in the audience have any.
Stop sharing to see your face because I cannot see your faces.
Yes, people are in disguise. But...
No questions. It was totally different.
So let me ask something.
Yes.
So I understand that you do mainly modeling, correct?
Yes.
But I was surprised about the data, and I was not clear to me what is the available data. You mentioned that you have only 1 point from the James Webb, and that's it all you have to test your models? Or, I mean, you mentioned the difficulty to get the data, but is that bad in terms of data availability? I mean, I don't know, I have no idea, but we cannot get a spectrum, for example, that we don't have the technology to get a proper spectrum of a rocky planet, either in a telescope on Earth or a space mission.
So for small rocky ones, they have some, for example, a famous exoplanet which is very, very close, which is rocky. It's big, it's bigger than Earth, it's rocky. It's super hot. It's called 55 Cancri, and they have many spectra from this one, right? But they haven't. People have claimed some papers that they found CO2, like so maybe it has an atmosphere there, but it's not completely solved. So because they are so faint, they are so small and so faint, you cannot take spectra from the current technology. Only from James Webb. They took for few of them, for example, from TRAPPIST, and it's only 1 point. Yes, so far. Now they have done 2 points.
But that's not a spectrum. That's just a photometric.
It's a photometry. Yes, it's a photometry. It's not a. You're right. It's a photometry. It's a photometry. So they have done only photometric points for a few of them, and well, they have a program which is called I don't know. Maybe Fran knows this program because they are trying to observe many. It's called hot rocks, something like this. So they have dedicated a lot of time from James Webb to this type of planets. But it's difficult. You cannot. The community is expecting these ground-based, very big telescopes, and then the next NASA flagship mission would be this Habitable Worlds Observatory, which this would be have some hope to observe spectra from actual.
So at this moment, you don't have data to compare to test your models.
No. At this point, we don't have many data to compare. No, not at all, basically.
But is it because people have not tried, or because the observatory is not capable of doing it within a reasonable amount of time?
No, people try because you see that even with one photometric point, people do a Nature paper just like this. You can see like dozens of Nature papers with only one photometric point. Then they have one paper in Nature with one photometric point. Then they take another photometric, then they take another Nature paper there. Frank can agree with this. So yeah, it's a very hot topic, but right now they are trying to take observational data from these planets just because they are small. And we are talking about the hotter ones, which they have temperatures which are hot.
Mm-hmm.
Yeah, so it's difficult. So here I'm not trying to claim anything big. We are trying to work and just draw a direction in the future, right? We don't do any big claims here. And some things, yes, are very theoretical, but I think can help us, with the observational strategies for the future.
Mm-hmm. Anyone else?
So one thing to ask you is that the jargon was completely different, right? Because you see that there is geochemistry there involved and there is atmospheric physics. So in reality, I have more common with the atmospheric physicists than with the astrophysicists.
And geophysics as well, right?
Geophysics, yeah, geochemistry. But the thing is, a real planet, especially a rocky planet, is very complex. So it's very interdisciplinary. You need to have some basis, especially if you want to model it, right? So you cannot only be an astronomer; you have to be a bit of everything.
Yes. No, I agree. I mean, the amount of fields put together in order to have a sensible model. I don't know if this is one of the questions I had. I mean, because you have shown many predictions from models, but are all these pieces, tied together? As in, is there you create a little model for every
No. Yes,
aspect that you want to reproduce, or you have a comprehensive, radiative transfer from the beginning to the end?
so that's the problem. That's the problem. That's the main problem. So imagine now you have a gas. Imagine Earth, right? If you don't include the radiative transfer, imagine so you release the gas from the volcano to the Earth. At the same time, the gas releases, the dynamics start playing a role, and then the radiation changes the chemistry and the chemistry change the radiation because the opacities, I mean, the constituents of the atmosphere will change. So they all have to play together. That's the problem. That's the difficulty of it. So you need to it's a very tedious modeling actually. But it's dominated from Earth, climate, and solar system. So I personally come from the solar system science. I was doing Mars and Jupiter. So in exoplanets, right now the community is a mixture of astrophysicists, planetary scientists come together because I tell you need that, especially in exoplanet atmospheres. Because the exoplanet detection, okay, you can be mostly an astronomer, no, because you have to.
And for the last part that you were saying that surprised me a little bit, that there is no biological signature that can not be reproduced by abiotic processes.
Yes, absolutely. So there is.
But okay, that is a statement very, very. I understand how that statement can come to be, but how many of those abiotic processes are really, really possible? I mean, because I understand that you were referring to some material that can be semiconductor, but how likely is that to happen in a planet, right? Because that matters, like the
Yes. So
not because it can exist, has to exist.
Yeah, okay, but at the same time, not because here on Earth it's life, just you.
For sure.
Right.
No,
So
of course.
you want to, for example, I tell you that there is this recent paper from this DMS, dimethyl sulfide, right, which became very famous in the media by a Cambridge professor, that says we detect in this sub-Neptune, I think Fran was sub-Neptune, they detect this constituent in the atmosphere, which on Earth is produced by phytoplankton. So, the media, of course, starts inflating and say, okay, now this is a signature of life, etc. Okay, another person came with a photochemical model like mine and say, no, I have found many pathways, for example, that I can produce this completely abiotically. So it's not the answer, but how do you draw the line? That's what I mean. I don't say that if you can produce it abiotically in your model, it's not life. But what I'm saying is that if you want to be secure, at least as a physicist, have knowledge of the baseline of the abiotic, of the capacity of the planet to produce abiotic signatures. And then imagine that you have thousands of rocky planets. You have to, some kind of at the same time, you have to filter fast the population. You have to filter a subsample, which is very interesting, fast, in order to go and spend resources to actually do very heavy characterization. I'm saying that if you want to filter very fast, you have to have, if you draw a line and you say, okay, this planet as a system has a capacity to produce signals abiotically of this parameter space, but you have a fast way to see that, yeah, but here is a deviation here, Okay, so then you can say, okay, maybe this is interesting. I don't say that if it's only a abiotic baseline signal, you will not have life. I'm not saying this, but so you have to have a way to categorize the exoplanets, and then also to have a way that before you go and make a bold statement that we found life, but you haven't yet completely understand what are because those exoplanets can be very different from us in a sense of their environments and chemical inventory, so they can do all of kind of things. And something final I want to tell you is that, first of all, imagine that we know life here on Earth as we know it, very Earth-centric. But universe, I accept that universe can be more creative than at least me. Maybe not from you, but at least me can be more creative. So how can you cover these exotic maybe forms? You cannot, right? So I think it's another way to, yeah.
Yeah, I know. I'm completely on board with the, remove ourselves of the anthropocentric thinking. At the same time, on the other side of the spectrum are these models that are capable of reproducing anything, right?
Yes.
It's like
Almost anything.
Give almost anything. Give me an observation. I will create a model that will reproduce it. And if you tell me with observations, no, but that model is not possible, then I will find another model that will be able, because the parameter space is so big.
Yeah, it
that
should.
It shouldn't.
But you know, you are a cosmologist, right? Or almost, you're a cosmologist.
Not cosmologist, but
do you do in your field like the Bayesian retrieval or inference
yes.
Bayesian statistics? So everything in Bayesian statistics is about the probability distribution. It's not
Yes.
certainty, right?
And the problem is always in the denominator, that
Yes.
that nobody cares about it, and it's all the possible models that can exist, right? But nobody knows. That's the problem always.
Yeah, and then you can compare models to them, and then you can see what kind of models your
Yes.
framework prefers, etc. With Occam's razor mentality, you know much better.
Yes.
But it's a probability. So you want to draw what is the probability distribution of this planet this and the other planet that, and of course here you have every exoplanet you study. It has to be Bayesian mentality, not frequentist, because you have only one chance.
Of course, yes.
For each one of them.
The problem is that we always operate with the numerator, right? Like that multiplication, but the denominator, nobody cares about it, because it's very difficult to know all the possible models that can reproduce that. And because it's everything that could reproduce
that. Just to make a comment this year, and we are running late maybe, but the biosignatures is not only on exoplanets, it's a very huge topic, for example, on the solar system and on Earth itself. For example, the question is, what is the oldest biosignature that you detect on Earth? This is a very interesting topic. It's very rich because it's so old, like billions, two and something billions of years, that you cannot do something like DNA. It's not possible. So what they do is the forms of the minerals. They have some shapes. So every time somebody wants to, say, okay, this is the oldest form of life, they realized afterwards that no, this was totally natural. Even if it has they do the same on Mars. You remember they found like a worm. Yes. So I think that this biosignal, and then we go back in history, the same was like with the early astronomers. Well, Mars has canals, and maybe there is life there. Mm-hmm. I think that in this research we are driven more like from an emotional perspective than we just sit down as we say, okay, just study the physical processes first. Mm-hmm. Let's see,
Yeah, no, it's a hand in hand. The observations rejecting models, then more models trying to reproduce observations is as long as you say, there are no bold claims without a little bit more investigation into possibilities, alternative scenarios. So it's very interesting. Very interesting. So anyone with more questions? Well, if not, let's. Thank you very much, Leo.
Thank you
for the talk. Very, very interesting. And let's see when you visit.
I hope next time I will be there physically, but you are very, let's say, isolated there.
Far away.
Paradise is paradise. If you want to come to paradise.
During the summertime, we are closer than during the winter time.
Yes, that's true. That's true.
The wheel changes.
In the summertime, you are the epicenter of Europe, but in the
Actually, thank you very much.
Bye. Thank you.
Harika, Leo.
Harika.